In the video, you will learn the Fibonacci series, the golden ratio, and how to apply the Fibonacci numbers to find supports and resistances. Leonardo Fibonacci was known as the greatest European mathematician of the Middle Ages. He was one of the first people to introduce the Hindu-Arabic numeric system into Europe and created the famous Fibonacci series. The series goes 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144, 233, and 377. The first thing we notice about this series of numbers is that each number is the sum of its previous two numbers. 8 plus 13 equal 21. 13 plus 21 equal 34. The next thing we notice is that if we divide any two numbers next to each other, we find that they are connected through the same ratio. 55 divided by 89 is equal to 0.618. 89 divided by 144 is 0.618. And 144 divided by 233 is 0.618. The same for 233 divided by 377. What about if we were to leave one number in the middle empty and now find the ratio between 144 and 377? We find the number 0.382. Now, if we were to divide the 0.382 by 0.618, again we would find 0.618. If we left a second number in the middle empty and we divided 89 by 377, we get another ratio, the 0.236. Again, if we divide 0.236 by 0.382, we get 0.618. What about now if we did the opposite calculation and divided 377 by 233? We would find another magic number, the 1.618. If we left a second number in the middle empty and divide 377 by 144, we find the ratio of 2.618. And if we leave a third number in the middle and divide 377 by 89, we get a 4.236. Again, the relationship between ratios continues, as 1.618 divided by 2.618 is 0.618, and 2.618 divided by 4.236 is 0.618 again. So what is this magic number that keeps on appearing throughout this series of numbers? This is a number that Pythagoras spoke about a long time before Fibonacci. Pythagoras stated that on any given line, there is a point on this line that is unique, not in the middle, a bit to the right. This point is unique because if you divide b with a, you will get the same number as when you divide a with a plus b, and that number is 0.618. The golden ratio, denoted as the Greek letter phi. Using the golden ratio, you create what Pythagoras called the golden rectangle. Let's see how. If we have a square with dimensions 2 by 2, starting from the middle point, draw a diagonal across the square to create a triangle. As Pythagoras stated, the length of this diagonal is equal to the square root of its other sides, which is 2.236. Now we are going to bring this diagonal line down and create a rectangle. So the distance of this line is 1 plus 2.236, which is equal to 3.236. So one of these sides is 2, the other is 3.236. If we divide 2 by 3.236, we find 0.618. Hence, we have created a golden rectangle. Now look at this. If we now draw a diagonal across the whole rectangle, where it crosses the line, it's again the golden ratio. Here we have another rectangle where the one side is 2 and the other side is 1.236. Now, if we divide 1.236 with 2, again we get the number 0.618. So again, we have a golden rectangle. Now we could draw another diagonal, and where it crosses the line, we will have another golden rectangle. And we can continue doing this forever, always creating a golden rectangle after a golden rectangle. Using this golden rectangle, we can create a golden spiral. A golden spiral moves by the number phi every 1/4 turn. That means if you take A over B, it is equal to 0.618. B over C is equal to 0.618, and so on. Do you know where we find this golden spiral and rectangle? We find them everywhere in nature. For example, the branches and roots of a tree extend based on the Fibonacci numbers and subsequently the number phi. The shape of a seashell takes the shape of a golden spiral. Another case is a photo of a hurricane from a satellite. How it takes the shape of a spiral, but it's not just any spiral, it's a golden spiral. The same applies if you fill your bathtub with water and let the water flow down the drain. It flows in the shape of a golden spiral. Where else do we find phi? Phi can be found in space. The galaxy follows the shape of a golden spiral. The human bodies that are considered perfect by other people are symmetrical based on phi. That means if you measure the distance from the floor to the belly button, and it is 1 meter, then from the belly button to the top of the head is 0.618 meter. This is the perfect body. Furthermore, this is a picture of our DNA. Well, our DNA is made up of golden rectangles. It is 21 by 34 angstroms. Phi is everywhere around us, in the plants, the animals, the galaxy, even in our DNA, and of course, the financial market. It has been observed that prices find supports and resistances at the Fibonacci ratios. Finding supports in an uptrend using Fibonacci. Draw Fibonacci from the all-time low to the all-time high, always from left to right. And use the 23.6, 38.2, and 61.8 as potential supports. For resistances in an uptrend, draw Fibonacci from the all-time high to the last bottom, always from left to right, and use the 161.8, 261.8, and the 423.6 levels for potential resistances. In the case of a downtrend, draw Fibonacci from the ATH to ATL, always from left to right. Use the 23.6%, 38.2%, and 61.8% levels for potential resistances. For supports in a downtrend, draw Fibonacci from the ATL to the last top, always from left to right, and use the 161.8%, 261.8%, and 423.6% levels for potential supports.